This example, which you could follow along in your textbook, is about the level that I might expect you to see on the AP test. The problem before that we just did, that's got some tricky things in it because you had to take the derivative with respect to time, but that required the chain rule and the product rule. Here, a different scenario. This is actually going to be, the trickiest part is going to be writing the equation that relates the three variables. But about the right level. So I have a police car that is chasing a bad guy. And the police car is coming toward the intersection. The bad guy has already gone through the intersection and turned 90 degrees. So, let's see. When, at the exact moment when the police car is here from the intersection and the bad guy is here from the intersection, we can use our radar gun and we find out that the distance between them is changing here at 20 miles an hour. The question is, can we figure out how fast the bad guy is going? What is the speed of the car? The car that's the bad guy who the police are chasing. So here it might be a little bit easier to write down our rates using our derivative notation after we sort of understand the scenario. So here we might draw the picture, but first you could write the things you know first too. So if this is north, then I have a police car that's coming toward the intersection from the north, so police car, and the bad guy has already turned the corner here and is headed toward the east. That's bad guy. And the distance between them, we can see that they have this right angle at the corner, this intersection. The distance between them is this distance here. So I'm going to call this P for policeman, B for bad guy, and D the distance between them. So now I know, I sort of got the picture. I'm going to write down the things I know. I know that the rate, let's do this. I'm going to call the distance between them capital D. I know that the distance between the two cars, the police car and the bad guy's car, which I called capital D, is increasing at 20 miles per hour. So I know that dt is 20 miles per hour. I know that the police car, what do I know about the police car? The police car is going 60 miles an hour. And I know which direction the police car is going. The police car is going toward the intersection. So notice here, because this is our first time, that means the distance P, the distance between the police car and the intersection, P, is getting smaller. That means that in this case, dp dt, the rate at which the distance P is changing is negative 60 miles per hour. If you use a positive 60 there, you won't get the right answer. Okay, and we can tell here the bad guy is moving away from the intersection, so B must be increasing. dB dt is positive. That would make sense because if dB dt was negative, that means the guy's turned around and is going back toward the police officer at the intersection. Other things we know, we care about, what do we care about? We care about dB dt. That's what we're looking for. And we're interested in that value at the exact moment when the police car is 0.6 of a mile north of the intersection and the bad guy's car is 0.8 miles to the east of the intersection. Okay, so big question. I'm supposed to be able to write an equation that relates D and P and B because those are the three variables whose rates I either know or I'm looking for. So, what do you think? Okay, ideally you'll come to the realization that this is a right triangle, and we know that the sums of the squares of the two sides, so p squared plus b squared, is going to always have to equal d squared. That's the equation I'm going to start with. All right, once I have my equation that relates all of the variables in the problem that I'm interested in, I'm going to differentiate both sides with respect to t. So how do I take the derivative of p squared? That's going to be 2p dp dt plus 2b dB dt is going to equal to d dt. So I've essentially taken the Pythagorean theorem with these three different variables, and I've differentiated both sides with respect to time. If you kind of are doing this in your head, you'll notice you could next divide both sides of the equation through by 2. Not required, but you could do that. So my next step, I'm going to plug in what I know. Remember, I'm trying to find dB dt, so I'm going to plug in what I know, and I'm going to isolate dB dt. So I filled in what I knew. I was so excited because I was going to solve for dB dt and I'd be finished, but then I was plugging things in and I got stuck because I didn't know what to plug in for D. Nobody told me how far apart the police cruiser and the bad guy are at the exact moment when they're traveling, when the distance between them is increasing at 20 miles per hour. So it's going to be our job here to use whatever math we know to figure out that distance. So I'm going to take a little side trip here, and I know that at the exact moment I'm talking about, this is 0.6 and this is 0.8, and you can use the Pythagorean theorem, or you can remember that 3, 4, 5 is a Pythagorean triple, so this is going to be 1 mile. So that's how I'm going to figure out this hypotenuse. Let me do that. So 0.6 squared plus 0.8 squared equals capital D squared. So 3.36 plus 0.64 equals D squared. So I get 1 equals D squared. That's how I decide that the distance must be 1 mile. So I'm going to plug that 1 in here. I'm going to simplify both sides. So I get negative 72 plus 1.6 dB dt equals 40. I'm going to add 72 to both sides. So 1.6 times, I'm just going to call it B prime for a second, equals 40 and 72, 112. I can divide both sides by 1.6 and I get B prime. So dB dt equals 70. So I would conclude that at the exact moment when all those things are happening, the speed of the bad guy is 70 miles per hour.